Well, welcome to this afternoon section. Artur Ávila graduated from IMPA in 2001, and he is now in France, in CNRS, and also at IMPA, part-time at IMPA, and he started his career in one-dimensional dynamics, which where he made several very deep contributions in a very competitive research area. And after a few years, he expanded his activities in several directions, using dynamical ideas to solve important problems in several areas, in particular in mathematical physics. And we are very proud that a former student of IMPA has reached such a high scientific standards. And today he is going to talk about chaoticity of Teichmüller flow.
So my topic will be, maybe I should start in the middle. So the first object to be defined are translation surface. Those are very simple to define objects. So basically, you start with a compact surface. With a very special kinds of atlas. So you have an atlas whose coordinate chains are translations. Translations. So it looks. So here it's a surface. So it has to be orientable automatically, but so here it is a little piece of the surface, and there is a shard which corresponds to some place in R2, and you know everything except by a modulo translation. So usually for manifold have diffeomorphic change of coordinates. Here is just translation. So there's well-defined directions, pieces of segments. There are well-defined angles and so on. There's a well-defined argument. So you have all this structure. So note that once you give this structure, you also give to the surface, you can pull back the metric from R2, and you get a flat metric. And then here the genus is bigger or equal than 1. So then you immediately see that should not be always like that, because with flat metric, the total curvature should be 0. So it should be only possible in the torus. So actually you have to allow for some singularities for this translation structure. So change the translation, except that you allow singularities, allow finitely many singularities. So here you have a Cartesian picture, and at a singularity you're going to have something slightly different, maybe like this, and with some angles and so on. So maybe like this, and with some crossings. So you have this structure with those singularities. So you get a flat metric, something that comes from this translation structure. You also get a choice of all the coordinates. You know what is east, west, north, south. So for me, it's enough to choose once and for all a parallel vector field. A unit parallel vector field pointing north. So this is a vertical vector field associated to the translation structure. And so you have this kind of geometric structure, that's the flat metric and so on. You also get some complex analytic structure. So those coordinates, the change of coordinates at translation, they are in particular holomorphic maps. So you get a Riemann surface structure. Plus, you actually can pull back the abelian differential, the one form that's dz, to here, because dz is invariant by translations. So you can also get a one form, holomorphic one form. And you have the zeros of this form at singularities. And they carry some curvature. So the other curvature of the surface is concentrated singularities with the weights related to the zeros. So related to the curvature order is related to curvature. Okay. So this is the complex analytic structure that's very convenient for this. So we are going to work at the space of those objects, so that we have to fix, instead of considering all translation surfaces with different genus, doesn't make much sense at first. Well, you might consider, but for us it's better to fix the genus, for instance, and fix the base combinatorial data when we discuss the families of such surfaces. That you can fix is like the genus G, and also the order of the zeros. Okay. So once you fix this, once you fix the genus G, for instance, you get what's called the moduli. So the space of such objects modulo isomorphism, which would be isomorphism of the translation structure or isomorphism of the flat metric and so on, presuming the parallel vector field, would be you get the moduli space of abelian differentials in genus G. And later you get a stratification of the space according to this further combinatorial data. For instance, you have this large space, and then there will be a large open set where the singularities are generic, so they are simple singularities, and then you're going to have higher codimension sets where you have a more degenerated surface up to very degenerate situation where you only have 1 0 with a very high order. So anyway, so this will contain so-called strata with fixed order of zeros. Order of zeros. So this is the ambient space where we want to work. I'll be more specific in a moment in an example. So just to get, so one more point, that I'm going to frequently work with normalized area. So because those objects you can always scale, you can scale the structure by composing with homotopy. So this will change the area of the surface. You can always try to work, this doesn't change much. So we can always fix, for simplicity, the area equals 1 of the surface. So we'll consider only the surface with area 1. Okay, so one very important additional structure is that it comes, this moduli space, it comes with a natural SL2R action that comes from the following. So you have this, the surface S, and then atlas of coordinates phi. So you have those charts. And given a matrix A belongs to SL2R, you can compose the chart. So you can do A composed with phi. So the same surface. So once you do this, you change the translation structure, And you are well, since SL2R is connected, you are deforming the translation structure, and you get this SL2R action. Since I made determinant equals 1 here, I preserve the area. So it preserves the normalization of the area. Okay, so now I can give the basic example, so that it's not too abstract. Is the simplest example, that's not actually what I'm going to talk about most of the time, is the case of genus 1. That's very important. It is, in this case, there are no zeros. Right? So those are just flat structures in the torus with some polarization. And in this case, you also get, since there's no combinatorics of zeros to consider, there's only one stratum. And what is it? Well, this is essentially, once you look at, so it's a space of torus with polarization. This gives the same as the space of orientable lattice with covolume 1. Because the volume of the torus is 1. The area is normalized to be 1, so that in R2. And this space is just a familiar SL2R over SL2Z, which is well known as the, well, for instance, it's the unit tangent bundle of the modular surface. Which it looks like this. Well, I don't know how to draw it very well, but people should be familiar with it. It's which should connect us, if I had chosen this direction, which should connect us to number theory. Right, so there will be a rich theory that we're not going to talk about. But this is just for us, this is just to have an idea of what kind of object it is. So we see that this moduli space is not too ugly. What do you see here? It's non-compact, it's a general feature. So those are, you see that it's moduli space. So now we are interested in this strata. Now, general picture should be some analytic variety. No, non-compact. Analytic variety. There are those kinds of special points here. Not too worried about them. It comes with some natural local coordinates, which I'm not going to describe, but the space doesn't come as abstract as it may look at first. Local coordinates. So you can make local parameterizations of this. Like this SL2R, and then you quotient SL2Z. It's a nice parameterization. This natural local coordinates gives a Lebesgue measure. Not a Lebesgue measure class, but actually some specific measure, which turns out to be, since everything is naturally defined, it's SL2R invariant. So you get all this extra structure. And everything is obvious here, right? For this, okay. Now, one thing that's different in the case of, in the general case with respect to this is that, well, not only you have several strata in each moduli space, but the strata can be disconnected. Any stratum can be disconnected, possibly. And then one possible topic of discussion that we're not going to follow is how to discuss how to classify the connected components. So how to identify the different strata and, well, say that, well, if there is one extra combinatorial data, maybe that has to be added to identify a connected component. So anyway, this is not what I'm going to do. I mentioned that this classification problem was work of Concepcius. Well, maybe I write for once the names. So they classified, and it can have at most 3 components. There are at most. Some are connected, but at the worst, 3 components. Okay. So, but now coming back to our main topic, what's the Teichmüller flow here? Like here, maybe not everybody can see. So Teichmüller flow is geodesic flow in this aspect. So Teichmüller flow is just the corresponds to the SL2R action. You consider the matrix of this type. So flow at time t. It acts by this matrix. So it's just the diagonal flow of the SL2R action. And this is what we're interested in. And so let me quote a theorem about this just to have a flavor. So this Teichmüller flow, it preserves the combinatorial structure, and since it's a continuous deformation, it preserves the connected components. So you can imagine that you have some funny space. Well, there is just geodesic flow in the modular surface. But here you have a general funny space, and a flow is something that does something like this. It goes around. You are supposed to already imagine that it's going to be a chaotic flow, so it's very confusing picture. But anyway, so you have this Teichmüller flow. I'm going to quote immediately one theorem about it, so to give a first condition that it is mixing up things around, is the following. Well, let me quote a theorem of Mazur and Veitch. First, about this measure there, they showed that the Lebesgue measure of a connected component, well, that let's say that Lebesgue measure of connected component of stratum is finite, right? So it is later on people computed this measure, so that it's possible to compute this exact measure. It was work of Eskini and Okunkov. But for us, it's not important. So there is this Lebesgue measure. I can then, once it's finite, I can normalize it. So I can consider a measure μ that's in each connected component. That's just Lebesgue measure restricted to the connected component, normalized by the mass. Right. So this I can do. Then I can state the second part of the theorem, that the Teichmüller flow is ergodic with respect to me. So in each connected component of a stratum, it is an ergodic flow. So what does it mean? It means only that, well, it means just that if you look at the behavior of a typical orbit, so if you look at almost every point in your modular space, well, first, it's going to go around all the space. It's going to smell the whole space. And it will do so, it will wind around the space, well, it will behave in the space to cover the space according to this measure μ. So essentially, if you look at spatial average, well, maybe right here, so ergodicity, you look at spatial average of the Teichmüller flow, integral 0 to t. So you look at you pick some function, some integral function here, phi, that's called observable. And then you do this, and you integrate, let's say, dx into dx dt. This converges. So if you take the average, the time average along the orbit, it will converge to the spatial average. So which is just integral over the connected integral phi dm. Right? So if you take the spatial average, you always get the same number for almost every initial condition, and it's given just by this this measure. Okay. Now, next point, which is actually quite abstract, is that ergodicity implies abstractly, it's equivalent to a stronger property called mixing, a priori stronger, so in view of the SL2R action. So I'm not going to discuss this exactly, but the presence of the SL2R action means that the Teichmüller flow has some extra property that allows to conclude mixing automatically, which is exactly the following. So that this is asymptotic loss of memory, or asymptotic independence. That can write like this. So if you look at integral phi OTT psi dmi is equal to integral phi converge integral psi. So what does it mean? So imagine that you are in your space. So what does it mean? If you don't know exactly where you are, you're around here with some probability distribution phi with some regularity. So you start your Teichmüller flow not from a well-known position, but with some uncertainty with respect to your position, and you run this Teichmüller flow for time t. So this is what I mean by this. So well, here I'm running by, so this should be psi, so maybe phi times psi. So essentially, so you run the flow by time t. No, it's exactly what was written. No, no, it's more or less. Maybe like this. T minus t. Okay. So you run your probability distribution for time t, and you look where you are, and you compare with some. You ask, for instance, if you are. Let's look at a little ball here, with whose characteristic function is psi, and you started by some cloud here, some probability distribution. So phi density of my initial position, and psi some localization, some localized observable. And I ask in time t, what's the probability that I am after time t? What's the probability that I'm located here? And the point is that asymptotically, well, this is a probability distribution. This is 1, and this is just the measure of the ball. So after a long time, I forget completely the initial probability distribution with respect to this. So originally I was not there, so probability was 0 at time 0. But after some time, anything that I had chosen will behave the same. So the density will be the same. So any initial probability distribution with sufficient regularity, I think that not much is necessary, will give the required. So this is what we call the asymptotic independence, or asymptotic loss of memory with respect to initial distribution. Now, so let me state a slightly stronger theorem that shows that this is actually, so now for a more recent theorem, is actually that this loss of memory happens very fast. So, so the theorem that I'm going to quote is called exponential mixing. Which is joint with Guezel and Yokos. It's in 2006. So it says that this convergence is exponential. So, so if you do integral phi OTT, it's exponential. If you assume that phi and psi are smooth and compactly supported. And analytically, this is related to some property called the spectral gap of the action. there is some Laplacian that can be defined, and there is some notion of a spectral gap. Okay, so this is more closely related to what in dynamics we usually mean by chaoticity. So there's a very fast loss of memory that it's useful to model, because it's usually very difficult to treat some very deterministic dynamics. So you usually need to understand it very precisely to be able to see, to understand the orbits, and most of the things you can say is that you cannot predict exactly how orbits will behave. But it turns out to be even better to know that you cannot say, to say very precise, that you can say very little about the precise behavior of each orbit. What's important is to know that it behaves like well, what's very helpful is to know that it behaves as a coin toss. So this is chaoticity. Usefulness in the analysis is to model the system as coin toss. I'm going to give some particular examples, but you essentially cannot say more about behavior of trajectory. You don't need to say more than just that, every new step of time behaves as if you had completely forgotten the past, and you're doing just a new coin toss and getting a new observable. Okay, so but to display this, I will give, so the point of the topic, of the talk, is to give particular example showing that this modeling can be used to answer some concrete questions instead of just some abstract dynamic properties. So, for instance, very interesting to know that there is this exponential loss of memory, but if I have some specific question, not a priori related to I don't know, to correlations between observables and so on, well, does it help anything to anyone to answer any question? Or just if I'm interested in computing correlations, it's useful. Okay, so the kind of question that interests me here for the examples is are dynamical questions also. So it happens when you look as so from this point of view, we take the Teichmüller flow as renormalization dynamics of the vertical flow. So the question that to be asked will be about some different objects, so not about what's going on in Teichmüller's on the moduli space, but some the objects that are modeled by, well, so the moduli space is space of translation surface. So what about some question about specific translation surface? So recall that you have this any fixed surface with translation structure, and you have a choice, remember, of a unit parallel vector field that goes like this. And then you can associate, you can consider the flow along this unit direction. There's a unit flow with unit speed in this direction. And so, for instance, in the torus, you just get a familiar translation of the torus, so not very surprising. So here, genus 1, you get translations of the torus, translation flows also. So which is quite simple to understand the dynamical properties. But the key point here is that, so what's renormalization here is so it's some general ideology that renormalization should be some fast dynamics. Some fast, and well, systems that we call fast usually, for instance, do systems with exponential loss of memory. So they very quickly they act very quickly on their objects, and they are used to as efficient method to study some slow dynamics. Well, sometimes it can be used. So some systems that can be renormalized, it's often an efficient method. So the kind of slow dynamics here, the translation of the torus is very slow and boring. Nothing much is happening. You can compute the iterates without any trouble, and there's no dispersion of the orbits and so on. So this is what I mean by slow dynamics, and then you use renormalization to understand it. So in the case of genus 1, some avatars of the normalization algorithm. So you have precisely the geodesic flow on the modular surface, and as we know, the study of the geodesic flow is related, for instance, to continued fraction algorithm and things like that. So you quickly get some well-known objects in this case. Here is a slightly less well-known. Where do I have this? Okay. So here, so how does it work, this translation? So you want to understand, well, so what you want to study is the long time behavior, of course. Of slow dynamics. So what you do here is that you originally consider a very long piece of trajectory. So now instead of consider time 1 is very easy to consider in dynamical system. You consider time very long, 1 million. So then the orbs are already very long and they made many turns around the surface. And what you do, you rescale by the Teichmüller flow. So Teichmüller flow, it scales the vertical direction, which now has a length 1 million. And after log 1 million time, you get a trajectory of size 1. So you recover a very decent time 1 map of some flow by applying this renormalization operator. So what looked like a very long time, now it's very short time, but you change your dynamical system. So what you do here, you change the structure on the surface. Now you consider a different surface that you acted for this time 1 million, but your time 1 million map now is just time 1 map. So so that's the idea of renormalization in this case. So it's very common in other fields, like in one-dimensional dynamics to understand the unimodal maps and so on. Also in, well, for rotations is also very used with the continued fraction algorithm. Okay, so one example of one of the first theorems that were proved using this ideology was the following. So what properties of renormalization reflect on some properties of this vertical flow. The ergodicity of the Teichmüller flow was seen by Mazur and Veitch, who were also the people that proved the ergodicity itself, that to imply the unique ergodicity of the vertical flow. For typically. So when I mean ergodicity of Teichmüller flow, it's with respect to some measure. So of course, what it will give us information is just things that are true for measure 1 sets. So for almost every translation surface, when you look at the vertical flow, the trajectories will be distributed with respect to the area in the surface. So you get this ergodicity of this other object for almost every parameter by the ergodicity of the Teichmüller flow. So this was one of the first consequences, but you see that ergodicity is not very strong. Chaoticity, well, it's some first step in the discussion of chaoticity, but it was not particularly strong. So what was interesting to mention in this talk were some more, what are the consequences of the stronger, chaotic properties. How the modeling of your flow by something very stochastic allows to prove certain concrete, to answer some concrete questions. So since I don't have much time, I'm going to concentrate, well, if there's time at the end, I'll concentrate, I'll mention something else, but I'll concentrate on one more simple to explain example with the concept-theoretic conjecture. The other is somewhat more complicated to explain. So the consequence that I want to discuss first is this concept-theoretic conjecture, which is, which can be formulated just in terms of the translational surface as before, but which will make intervene the Teichmüller flow in a second. So this concept-theoretic conjecture, it says something about something called the Zorich phenomenon, which is something very pleasant to describe. Which is the following. So the point here is that you have your surface, and now you have this orbit that's very long. I already said something about this orbit, that this orbit is going to be distributed with respect to that measure, but you see that it's getting is twisting around the surface, is making many turns in around this. Well, there's this handle here, and it starts turning around this handle, and does stuff like this. Well, it's just an example. But so you could ask not about the distribution, but you could ask how much this long piece of trajectory is winding around the surface. So how it's going around all those loops. So you ask how is the long piece of trajectory winding up, winding around the surface. So this kind of question was asked, well, so one basic reference for this kind of question is a paper of Schwartzman. And well, what's common to consider is the following. So you have a very long piece of trajectory. It's too long here. So you have a somewhat long piece of trajectory, and it's an open piece of trajectory. Then you connect it to the initial point, so it started at this point x, it ended up here. If it had closed, then fine, but in practice here it's not going to close, so it ends after some long time. I truncate the trajectory, and I close by some short segment. So we had the gamma t long piece of trajectory, so time t trajectory segment of length t. And then I close it, is obtained by somewhat arbitrary closing. Okay, I'm going to be interested in so mistake that's created by considering a different way of closing it, as long as I close by a segment of length bounded by diameter of the surface, is going to be a bounded error. That's not very important in the questions that I'm going to ask. So anyway, you consider this new trajectory, and the way you measure one way to measure how this trajectory is going around the surface, all those handles and stuff. So one way to do this is just to consider the homology class of this belonging to H1 of the surface with coefficients which happens to have integral coefficients. So this is just a closed loop. So we associate to this segment of trajectory homology class. So now you are interested in the long-term behavior. So the question is, for instance, what happens to this gamma t when t goes to infinity? So the basic answer already in Schwartzman that applied here gives that gamma t over t. So if you normalize this, there is some asymptotic direction in homology. So now with real coefficients, because your coefficient, no, it converges to some c. So if you look at this very long piece of trajectory, it's roughly just, well, so this means it's just CT in some sense. So the trajectory is going, so there's the homology that you imagine that's a space, well, it's, in genus 2, for instance, is a space of dimension 4. And you're just following some line in this direction here with some speed. That's just the norm of this vector. And you're going that direction in the homology. Now, this is the first answer that's given. This C, by the way, is usually non-vanishing. And so what Zorit studied, so the Zorit phenomenon was something discovered by Zorit, that wanted to study in more detail the behavior of this sequence. And what he found was very surprising at first. So first, in genus 1, the answer is completely obvious. So essentially, the torus is even difficult to explain because you can confuse the homology for the space itself, because it's just Artur, the fundamental cover, and Artur is the homology, and so on. But anyway, if you have, imagine that you have a square lattice, like here, and then you have a direction going here, and with unit speed. So the asymptotic cycle is just this direction. If you identify the R2 with the homology, H1 with real coefficients, this direction that you're following is just what you're doing, and everything's quite obvious that it behaves like this. And so you see that in the torus, everything's easy to compute. And you see that the mistake that you do here, so if you do 1 over t gamma t minus ct, for instance. So the mistake, so error in asymptotics, error in the asymptotics is bounded. So the asymptotic, this, well, everything's quite simple, but this formula gives very precisely the asymptotic cycle at time t. So everything's very precise, but something surprising happened already in genus 2. So he took he made a computer experiment, so he took a random surface to do his computer experiment, and he notes that there is some polynomial error. Well, polynomial deviation, which means that if you do 1 over t, let us say gamma t minus, let's say the line passing through C, the distance from this to here, is no longer bounded, but has some oscillates with amplitude. So there's some way to formulate, but amplitude t to some exponent lambda that I call lambda 2 for some 0 less than lambda 2 less than 1.
You don't have the 1 over t there.
Yes, thank you. Yeah. So just the difference, the distance from here to here. It oscillates with some amplitude. So it is less than t, so this has roughly size t, so it's less than t, is more than bounded, and there is some precise exponent where lambda 2 is constant almost everywhere, according to, as much as a computer experiment I can say this, constant almost everywhere in the connected component of stratum. So this is the fact that lambda 2 is constant almost everywhere in the connected component stratum is not that surprising, because after all, it's easy to see that it's a Teichmüller flow invariant, and ergo this means as answer that you cannot have two things that are Teichmüller flow invariant in sets of positive measure. So once lambda 2, well, for the way it's defined, it's obvious that. So interesting thing mostly is that the deviation exponent is strictly between 0 and 1. There's something else that's interesting, but not difficult to prove once you have everything in place, but is interesting nonetheless, is that this deviation doesn't happen in all directions. So you have this line that's asymptotic, and you are going in the direction of this line, more or less, with some error that's not too small. But your space in genus 2 is 4-dimensional. So, so you have this line that you're trying to follow, and then there is a 3-dimensional section transversal that you could be spreading around roughly a priori anywhere with this amplitude, but something more precise than this. So the oscillations happen along a 2-plane containing RC. No? So this is obvious that should contain it. So you see that there is a 2-plane F2 containing RC equals F1. So you have a first direction that's asymptotic, and then you make a mistake that's somewhat large, but along some 2-dimensional plane, and the error that that happens outside this plane. So so if you look at this, the oscillation around this plane now, F2, now this is going to be bounded. So then, so after this, you reduce the case of, well, it's like in genus 1, or there was some asymptotic direction now plane where the mistakes are bounded, so, which is quite interesting. And then you see that then you do the experiment in higher genus, and then you do genus 3. Then you're going to see the similar picture that there are going to be the distance between gamma t and F1, that CR is going to oscillate as amplitude. T to the lambda 2. Then the same thing with F2. There will be some amplitude with some different exponent. So what's going to happen is now that there's a 2-plane where most of the oscillation happens, actually. So there'll be a good 2-plane. But it will not, so the mistake when you consider this distance to this 2-plane is still large, but smaller than the total amplitude. So there's some stratification happening. And with some exponent 0, less than lambda 3, less than lambda 2, less than 1 here, this time. So there's going to be some first mistake, amplitude to lambda 2. Then you look more carefully and you see that there is a secondary mistake with amplitude t lambda 3. And you see that the mistake after this, when you look, this secondary mistake will be concentrated around some 3-dimensional space, and the mistake for this will be bounded now. So same things here, right? So the distance to F2 will be some secondary mistake, and then this secondary mistake will be concentrated around the 3-dimensional space, and this mistake now will be bounded. And we are going to have F1 contained in F2, contained in F3, and the dimensions are 1, 2, 3. And the general picture is exactly the same. So in genus G, there will be a sequence. So so the asymptotic behavior of this sequence of cycles is described by what's called the asymptotic flag. F1 contained in Fg, and associated deviation spectrum. Zero less than lambda g, less than lambda 2, less than 1. So you have this spectrum of deviations that appear. So this is very well supported by numerics, and Zorit himself and together with Concept immediately tried to find some proof of this result, and they related it quite fast with the Teichmüller flow. So how to understand that there should be some picture of asymptotic flag arising. Where does it come from? It comes precisely from the normalization, and links us soon to chaoticity, will be used to understand exactly this, how to prove things about this, these objects. But the first picture that we have is how to understand this, how this should arise in terms of renormalization. So what matters here is look at the renormalization action. So everything here is concerned with homologous behavior of vertical direction. So renormalization action. So as I said, you take a very long piece of trajectory, apply the renormalization flow, the renormalization flow, so you apply the Teichmüller flow, and you get a short piece of trajectory. That's fine. But in doing so, you need to keep track, in order to obtain this, of what this is doing with the homology of your space. Action on homology. Let me explain. So start with your surface, and then you start to deform it. So the metric now in original coordinates looks very bad. So you had, well, what you used to call a segment of size 1 became a very short segment. What you used to call a horizontal segment of size 1 is now a very long horizontal segment. So original coordinates are very twisted. And if you look at, when you look at a surface, you usually identify, when I draw a surface here, I'm identifying some particular presentation of the homology. There are immediately clear some segments, some cycles that are short geodesic segments. When I draw like this, it's immediately clear that there is some better loops than others. So I have this kind of loops and this kind of loops and so on. This one is trivial in the homology, but whatever. So there is several loops that are very clear when I draw the picture that are just better than the others. I could also draw a simple non-intersecting curve, which is extremely long, and but when I draw this picture, nobody's thinking about this particular presentation. So what's going on is that after I let the Teichmüller flow act on my surface, all my curves that were originally considered short, of size less than 10, now they became very long. And, but this doesn't mean that the surface became awful. Just that the original way to look at it became bad. So if you look at the modular surface, what's going on is that even after applying a long time of my Teichmüller flow here, I often, well, there is some traveling towards the cusp, but this doesn't sometimes return. And then you know that you are in some compact part of your space. So there is recurrence anyway. So this recurrence is translated in the fact that the measure is finite. So points are coming back by point recurrence. So from time to time, actually quite frequently, you know that your surface has some way of looking at it that is nice. So the point is to identify the new base of cycles that are short, that are reasonable. So what means that after applying a long time, I look at my surface, it looks very distorted. But I know that if I apply some different marking of the surface, it will look just fine. So this different marking means, when I say look at a different marking, it means apply. So you need to apply some element of mapping class group. So some strange homeomorphism of the surface that change the marking all around. Mapping class group. To get back to some nice surface. Now, when you apply this nice homeomorphism, F from the surface to itself, so just some changing of marking, it has some action in the homology. H1 of S to itself. Okay. So the point is essentially that so you're going to get some strange matrix acting in this space, and essentially what turns what comes around is that I want to describe geometrically how this matrix acting. So what I look at is what it does with a standard sphere in my space. It will take, as any matrix does, well, it is inversible matrix because it's homomorphism. It takes my sphere to a very, well, in general, it takes some sphere to some ellipsoid. So this ellipsoid has some axis. So there's some long axis, and then there is going to be shorter axis, and so on. So the length of the first axis is going to be exponential t. Remember that I have to understand orbit segment of size big T, capital T, I need to apply the Teichmüller flow for time log capital T. So in any case, this is going to happen like this. And then there are the so-called singular values of the matrix that are going to be the secondary x that's going to happen. Maybe there will be something called exponential lambda 2t, a little bit smaller, and there'll be a third x, and so on. Total volume of this, there's some reason to, this is a symplectic matrix. Total volume of this ellipsoid is 1. So there's some symmetry also in this picture. Anyway, what happens that what becomes quite fundamental in the picture, what did I write? Is, okay. So what becomes quite fundamental in the picture is to understand this sequence of coordinate changes. So in particular, so it's precisely the sequence of matrix acting on homology. So for longer and longer pieces of trajectory, there'll be more and more complicated matrices. And what we do to exploit the chaoticity is write this long matrix F star, that's this very complicated homeomorphism to change the marking all at once, as a sequence of, so this matrix of F star can be seen as a product of matrix. With subtension like this. You take your surface, and then you let it degenerate, becomes ugly, and I don't wait until my time t to change it back to a nice to a nice surface. I look at the first time that I can change it back to some decent surface, and then I consider the associated homeomorphism, so I write F star is going to be a sequence that, well, my F is going to be a sequence F1, F2, Fn. Every time that I can change my surface back to some decent picture, I do. And then I have discrete moments when I can do that. And in doing so, I get my matrix F star will be, or which I call A, N, will be a sequence of obtained as a product of matrix A1, A2, AN. So I write my very long matrix, very complicated matrix that I'm going to say that is going to have very complicated singular values as just a product of many simple matrices, relatively simple matrices. So now the main point here is that the chaoticity of the Teichmüller flow and associated objects, so chaoticity, means that this sequence of matrices looks like a sequence obtained by coin tossing. So in fact, there are countably many possibilities for those matrices, a little bit more complicated. So you have a coin with countable many faces. But chaoticity means that it's very difficult to distinguish what you obtain in an actual random orbit that you take from what you get at a complete random coin toss. So this means that the sequence of matrix behave as independent. And now, so the basic point now is to, I can write the following, that, well, I need to go a little bit fast here, but essentially, this picture here say that a simple spectrum, well, so first, the fact that you write this as a product of matrices means that there is asymptotics. There's Osseledet's theorem. But means that there is an asymptotic spectrum. Anytime that you write, since you view your complicated matrix as a product of many matrices that are obtained in a deterministic fashion, albeit a little bit stochastically, there is an asymptotic spectrum here, Lyapunov spectrum. with exactly this thing, that there is going to be a major x that turns out to have a Lyapunov exponent 1, but there is a secondary x which will have some Lyapunov exponent that's going to be lambda 2, and the third, and so on. So there's some asymptotic behavior, and concept Zorit related the Lyapunov spectrum and the asymptotic flag. Essentially, they said that if associated to those large matrices, you get a sequence of so-called Lyapunov exponents, lambda 1 equals 1, bigger or equal than lambda 2, bigger or equal than so on, bigger or equal than lambda g, and bigger or equal than 0, and then there's something else. And essentially, they said that if there is not some degeneration, so this is abstract, just because I have a product of matrices. But if all the inequalities are equalities, so in case of simplicity, implies the asymptotic flag. The asymptotic description of Zorit. So if you can prove that this Lyapunov spectrum is simple, that there's no degeneration of different eigenvalues, so that all the different axes, they are all very different one from the other. There's no kind of similar looking axis. Now, so just to conclude, the way how it's useful to know chaoticity is that there's some very general fact that that the generic picture, so if you have random numbers that you pick up, that they should not be, they should be all distinct, right? So it turns out that indeed chaoticity plus enough richness of the sequence of matrix implies simple spectrum. And use the concept Zorit, so this was the concept Zorit conjecture. And these implications prove the concept in Zorit. So the chaoticity plus richness implies simple spectrum. This means that essentially if you have actually have a random product, but all matrices are the same, it still classifies as a random product, but actually you cannot say anything, so it's not really chaotic. But if there is enough variation among those matrices, if it really sees very different aspects of the space of matrices, then which is the generic picture, then chaoticity can be used to imply simple spectrum. Right? So there's some condition that can be verified with finitely many matrices here that appear in this random product that imply that the Lyapunov spectrum is simple. So this gives a way to use, so the point is that how to use chaoticity. Once you know that the Teichmüller flow is chaotic, the immediate idea to prove the concept Zorit conjecture is to show, so it reduces essentially to prove that you have enough richness of the sequence of matrices, that you see very distinct matrices. This is a problem in itself, which is not easy, but essentially, that's the only proof that exists. So that the most efficient method is exactly to look at to prove this richness picture, which is proved by actually looking at some kind of boundary behavior of the cocycle. But this is just one example that you have a problem that's a priori very far from what I initially defined as chaoticity, was just some asymptotic loss of memory, so that you forget where you are. So I defined here the Zorit phenomenon, which is an observation that apparently not related to renormalization, and it's an observation that has some very specific predictions about the whole family of dynamical systems, and it can be understood easily in terms of renormalization. So renormalization already implies a big part of the picture, and but the specific point, which is the simplest of spectrum, can be proved by showing that by using the chaoticity of the Teichmüller flow to model the particular dynamics that are going to appear as an independent process, and applying some general criterion, well, some general theory of independent process. And then you need some extra specific features of your flow that I'm not going to talk about because I'm already over time, but it can be applied in different aspects also of the theory. I hope that many more applications of chaoticity, this kind of theorem and a previous theorem that I did with Giovanni Forni were first applications of really mixing properties of Teichmüller flow. Original applications of the renormalization were more concentrated on more elementary aspects like ergodicity. So just the fact that it sees the whole space. But the fact that you see the whole space as if it was randomly sampling it with much stronger property, I hope that you have stronger applications in the future. Okay.
Any questions or comments? Okay. Let us thank Artur again.